So I would like to call Mr. Thodoris Katopodis as our next speaker. So Thodoris Katopodis is a senior manager in EY Business Consulting Department, and he has a subject matter knowledge and 9 years of experience in climate change risks, vulnerability and resilience assessment in business and scientific community. He holds a diploma in mechanical engineering from the University of Patras, an MSc in energy systems and renewable energy technologies from West Attica and Hero-Watt universities, and a PhD in mechanical engineering from the University of Patras in business continuity, resilience and adaptation of all refineries to climate change, funded by the Industrial Research Fellowship Program at NCSR, Demokritos, under the Stavros National Foundation and a grant. And his topic is going to be how to address requirements for physical climate risks to enhance building resilience. And as soon as Dimitris will resolve
it froze, I think that it froze.
Okay.
Engineering tracks.
Yeah, we did it. Thank you very much.
Hello everyone. Thank you so much for being here today with you. Yes. In this topic, we discussed how to address requirement for physical climate risks to enhance building resilience. This presentation will start with a small introduction to climate change and to impacts, indicative disruption caused by extreme weather events across the supply chain of building sector will be presented. Evolution in standards and regulations are also presented, and we conclude on the required holistic methodological approach in order to meet the requirements from a climate risk analysis perspective in order to build resilience. As previously mentioned, one of the most noticeable changes detected as a result of recent warming is the increase in extreme weather events. Over the last decades, weather patterns have become more variable, with more frequent and more intense events. As the frequency and severity of these extreme weather events increase, impacts of climate change are anticipated to become stronger in the future, leading to higher costs and more accidents to economy, to infrastructures, and to people. Greece is gradually getting a warmer and drier climate. During the last decade, prolonged heat waves are associated with thermal stress events, both on people and systems and infrastructure, and also are linked with severe wildfires. During the last decade, more than 10 billion of square meters of the Greek area have been burned, and properties and people are actually affected. On the other hand, medicanes, which are extreme hydrometeorological phenomena characterized by high wind speeds, intense rainfall, and dangerous flooding events, have also become more frequent. In the recent past, xenon, Zoba, Cyanos, and most recently Daniel caused widespread economic and social impacts, and even loss of human lives. Daniel was the event with the multiple losses and impacts across different sectors and across, of course, the value chain, affecting properties and buildings of many companies. In this slide, indicative disruptions caused by extreme weather events across the value chain of the building sector are presented. These impacts affect the physical properties of buildings and the direct operation, stressing building structures, exposing electrochemical equipment, damaging properties, but also affecting the whole value chain from upstream to downstream, with potential damages to the interconnected infrastructures, impacts in the logistics and to the supply chain of raw materials, delays in the delivery of newly construction projects, up to impacts on employees, higher repair and maintenance costs, or even increases in the insurance costs. So, the increasing frequency of extreme weather events and loss of biodiversity increase the risk profile of companies. According to the World Economic Forum, climate change is costing the world 16 million per hour and is estimated to be between 1.7 trillion and 3.1 trillion per year by 2050. Therefore, climate preparedness is becoming a strategic priority across the value chain and requires fundamental long-term investments and planning, holistic methodological approaches and adaptation measures. Although investors, consumers, organizations and government have taken first steps and started considering the shift towards sustainability, this shift is mainly driven by a wide range of climate-related legislation and regulations, and also existing voluntary frameworks, as they already impose measures requiring companies to report more actively and to adopt holistic approaches. For example, the Corporate Sustainability Reporting Directive requires large companies and listed companies to publish regular reports on the social and environmental risks they face. Requires also to report on how their activities impact people and the environment. For example, among the set of European Sustainability Reporting Standards, ESRS, ESRS E1 is the climate change topic which requires an organization to publish adaptation plans for the significant economic impacts associated with climate change, to disclose relevant climate change performance associated with their performance and their carbon footprint, and to disclose also and to publish their material climate risk and opportunities and their potential financial effects. On the other hand, the EU taxonomy regulation, which defines when economic activity is considered as sustainable, requires, in order to align the activities, to demonstrate that the activities are resilient to material climate-related risks. And additionally, existing voluntary reporting frameworks, such as the TCFD-IFRS and the Carbon Disclosure Project, recommends companies to disclose information on governance, strategy, risk management, and metrics and targets, and also to disclose information about their scenario analysis around climate change, both in mitigation and adaptation. However, building climate resilience is required not only to meet the previous mentioned specific regulatory requirements, but it is highly recommended for companies in order to have the capacity to anticipate climate risks, to absorb shocks and stresses in order to continue operating. In that event, there is a need for a detailed and a granular climate risk assessment methodology and of a detailed plan of action with specific adaptation measures in order to reduce risk and to build resilience. In that perspective, holistic approaches need to start with a physical climate risk identification to identify their material and physical risks, to use the most recent climate scenarios and the most appropriate climate indicators, to perform climate statistical analysis in order to estimate the likelihood of occurrence of these hazardous events at specific locations, and then to estimate the severity of impacts across relevant categories in order to quantify the financial impacts of the material risk. And finally, to propose a detailed plan of action with specific adaptation measures for assets and activities, and then to set their resilience plan. So, risk assessment process works by assessing the likelihood and severity of the impacts. The part of the likelihood looks at how likely the identified climate hazards are to occur within a given time scale, considering also the lifetime of the project. It can be determined thanks to hazard indicators, can be computed based on the projections of climate models, and throughout the statistical climate analysis can be identified their average, minimum, maximum values and their return period. And also the part of the impact assessment can be determined either qualitatively or quantitatively thanks to damage functions, which in fact map the hazard intensity to the expected percentage of loss. So, in this slide, we refer to a specific case study we have run in the past, trying to estimate the financial impact of floods to building in the broader Greek area. Shows the modeling approach that was followed, climate scenario and climate parameter that was taken into consideration. And then we conclude with the estimation of the financial impact using specific damage functions, both for existing and future conditions. I would like to mention that the use of damage function can facilitate the quantification of the financial impact as it correlates the hazard intensity with the expected percentage of loss. And just to conclude with what is needed in order to set a proper resilience strategy, climate resilience is basically a forward-looking process and requires holistic approaches in order to deal with those physical climate risks. This process requires a set of proactive and reactive actions. Both here and the next page, indicative actions based on best practices as found in scientific community peer review analysis and European recommendation are presented. So proactive measures here and actions must identify, monitor and always evaluate the potential adaptation options. Need to proceed on infrastructure improvements, invest in backup power systems such as generator or UPS. Need to have an emergency planning and response through diversifying suppliers. Conduct regular trainings to ensure that employees are aware of how to react in the event of an emergency. Invest in sustainable practices and technologies and review, update, or develop if resilience strategies are not in place, based on new technologies and lessons learned. While on the other hand, reactive strategies need to activate emergency response plan, to establish better communication process, need to assess the damages, to implement the business continuity plan in order to resume critical operation, to establish a better financial management with a better allocation of resources, to ensure cleanup or repair work, or even to provide support and counseling services to employees who may be affected by the disaster, to be able to comply with regulations and to update regularly emergency response and business continuity plans based on lessons learned. However, the required actions don't stop here. Addressing the impacts and risks posed by climate change requires adaptation strategies to consider wider systems and level factors, from capital providers and government regulators, up to suppliers, infrastructure and customers, as well as ecosystem services to local communities. Needs also multi-level coordination, sufficient and trained personnel, financial resources, and continuous monitoring and evaluation of the implementation process. Thank you.
Thank you very much for your presentation. Before any questions, I'll let you know that the first question is on Slido, so please give us your evaluation. So, any questions, please?
Thank you, Thodoris. That was very interesting. So I picked two parts of your presentation. I would like to very briefly join and ask you a single question. So one was about very useful slide about the EU taxonomy, and the other ongoing regulations or guidelines. That's the one. Yeah. So in my field of work, I come from a perspective of trying to decarbonize the building sector, which is a part of the climate assessment that we're talking about. So one of the first two boxes there would expect organizations to run something like a CREM analysis, the carbon risk real estate assessment method, that requires a prediction about the future, how the grid is going to decarbonize, what the expected temperatures is going to be like, which ties in very well with the modeling that you showed us. And I want to sort of share my frustration and ask your view on this. In your field of work, do you think there's enough data to accurately project and predict what's going to happen in the future in the grid context? Do we need something more like what Anastasia previously mentioned, like a specific, in the grid context, future projection, like a climate change adapted weather file for dynamic simulations in the building and the wider engineering sector? Did that make sense?
Yeah, I mean, okay, these disclosures are mostly publish the previous year assessments, even in the carbon footprint analysis, even on targets and on performance on climate risk analysis. But project changes need to be assessed with using, of course, scenario analysis. In that perspective, scientific community facilitate that process with modeling and specific projections. But of course, I think every 5 years, not at regular periods, need to be. It's a process that always happens. Need to be assessed and reevaluate the results and the analysis. Maybe Mr. Dr. Thodoris.
Sorry. Before that, no, you are allowed. Don't worry. But before that, we move to the next question as well. Just that. Sorry.
Just a quick response, but because I think this is a great question. We're designing, we're constructing with the wrong data. All right? Because even the weather data that a mechanical engineer would use is past averages of the decade or 20 years. And what we're seeing now is going the other way. So even the fundamental calculation before we go to simulation, whatever it is, we need basic information we use, like weather data, to be reconsidered, designing for the future, not the past.
Thank you about that. Another question? Okay, are we okay with the answers? Okay, thank you very much.